Here's a little tour of singularities, so special, usually bad points, and smooth points of various mappings. And this is in R, R2, R3. And the idea is we're going to look at some examples and try to get a general idea of when can we predict that something weird is going to happen qualitatively with a mapping. When are we going to get a singularity, and why would we care? Okay, so our first example is going to be a function from R1 to R2. So we're going to classify these examples as either small to big, big to small, or equal. Let's go from a smaller space to a bigger space. And it's going to be f of t equals t cubed t squared. And so that's a parametrized curve. And we've seen it before, and you can plot it yourself. It has a cusp right here, if that's x and y. And that's where t equals 0. Okay? And that's a little surprising because these functions individually, these are smooth functions. And smooth for me just means, basically means differentiable. It often means really differentiable or infinitely differentiable. For me, it's going to just mean differentiable. Okay. So why is there a cusp here? Well, we've talked about this in our class, and hopefully you've seen this as well before. There is something bad about this at the origin, at t equals 0. And you can get it by looking at the derivative, the velocity vector, 3t squared 2t, and that becomes 0, 0 when t equals 0. Now I'm going to actually write that as a column vector, because if you have a little more advanced presentation, then this is really the matrix of derivatives. It's often called df. Sometimes it's just called f prime as well. It's the matrix of derivatives, and it actually should be a column vector. That makes sense if we know any linear algebra, because a linear function from R1 to R2 is going to have a matrix that is 2 outputs, that's 2 rows, by 1 input, that's 1 column. And so the matrix really should be this guy. And in this case, you get the 0 matrix. Okay, so let's list what we could expect of a 2 by 1 matrix and what's special about this guy. So 2 by 1, it could be a 1-to-1 matrix. And in general, if I just look at the general form, 3t squared 2t, that's just going to be some non-zero vector. If I think of that as a linear transformation from R1 to R2, that is going to be 1-to-1. Okay, but f prime of 0 is not 1-to-1. That is something that is special about it. It's the 0 matrix, in fact, 0 vector. But in terms of qualitative things about matrices and transformations, which I want to emphasize in this video, this derivative matrix is not 1-to-1, whereas it could have been. And at every other point, it is 1-to-1. And let's just note, it could never be onto. You're not going to get a linear map from R1 to R2. At most, it's going to fill out a line. It's not going to be onto. So this can't be, the lack of onto-ness of this transformation can't be what's going wrong with it. But it's plausible that we could focus on saying, hey, it's not 1-to-1. The derivative matrix is not 1-to-1. Maybe that's sort of going to fit into a general scheme about a reason why we might see a bad point. Okay. Another way to say it, if we want to think about the rows and columns, things like that, this has only one column, but we could say in a sort of overly fancy way, the columns are not linearly independent. Let me squeeze that in over here. Columns not linearly independent. And if you think back to the linear algebra, that is really exactly when a matrix, the transformation is not 1-to-1. It's when the columns are not linearly independent. Okay, so that's a simple example from R1 to R2. Now, what about, where's my eraser? Here we are. The next simplest case would be R2 to R1. Okay, so example 2, let's use another color because that's losing the potency on that one. F from R2 to R1. Ooh, that's big to small. That's going to have a bit of a different flavor. Okay. And it's going to be f of xy equals x times y. Okay. Let's see. Actually, in order to fit in with, I think I'm going to modify this. This is not how I did it in class, but let's say x squared minus y squared. Okay. So, in the previous example, I was looking at the image. That's another thing I should have said about the small to big example. With this example of the curve, I was looking at the image. I was looking at the outputs of this guy. If I had looked at a level set, like the set of t's where f of t equals some particular, like, 3, 2 or something, that would either be just a single number or not, or maybe 2 numbers or something like that. It's not very interesting, okay? So the inputs were not particularly interesting, and that's typical when we go small to big. We don't really focus on the inputs so much. It was the outputs, the image of this curve, all the outputs of f of t that was interesting. Here it's going to be opposite, okay? So instead of having that situation, which I should have put on the earlier board, I'm going to look at the inputs. That's more interesting. If I just look at what numbers are the outputs of this, it's not that interesting. In fact, it's just all possible real numbers. You can easily get any possible real number from this. But the inputs, that brings us to level curves. Oh yeah, we do that all the time for a function of 2 variables. Okay, so we're going to draw the level curves. Well, x squared minus y squared equals 1 is just a hyperbola. If it's equal to minus 1, it's the conjugate hyperbola. If it's equal to 2, it's like this, or minus 2. But there's one special example, x squared minus y squared equals 0. That's where x is plus or minus y. Aha! There's something quite different about that. All these other level curves for 1, 2, minus 1, minus 2, if I look at a microscope, around this point, it's going to look like some nice, smooth curve. And in fact, if I really magnify it, it's going to start to look like exactly one straight line. That's what happens with smooth functions, smooth curves. They start to look straight the smaller you get. This guy, if I put the microscope right here on the x, that's never ever going to look like a single, straight, smooth line. And that's quite different. So that is special. It is unique. So we call it a singularity. And what we're really focusing on it is not just that it's different in some random way, it's that it's not smooth. Not a smooth point. And smooth here means that if you put the microscope on it, it looks like just a nice, slightly bendy curve. And if you put the microscope really, really tight, high magnification, that actually looks like one straight line. Okay, so it's right at the origin that's going wrong. So the origin seems to be the bad point here. Well, let's look at the matrix of derivatives of this guy. Okay, f prime, or df, that's going to be, there's one output, 2 inputs. And so that's just going to be df dx, df dy. That's the matrix of derivatives here. df dx is 2x, df dy is minus 2y. Aha! So at the origin, that's going to be the 0 matrix. Aha! Now, I don't want to erase all of this, but I really need to erase a lot of it. Okay. Let me just erase everything but this. Okay. So f prime of xy is this guy, f prime of 0, 0. That's not very good f. Is the 0 matrix. Okay. So once again, if x and y were not both 0, this is going to be a nice matrix that's not just the 0 matrix, and in particular doesn't have the special properties that this one has. So let's look at what is special about the 0, 0. I don't really need a comma there. Okay. It's not, if I look at it as a transformation, it's not onto. Okay. It's also not 1-to-1, but even the general matrix, if I put in like x equals 2, y equals 4, that's not going to be a 1-to-1 transformation. We never have, from big to small, for a linear transformation, we never expect one-to-one. It doesn't happen. It's impossible. Okay, so it's not the one-to-oneness, the lack of one-to-oneness about this zero matrix is special. It seems to be maybe the lack of onto-ness. Okay, or another way to say it is that the columns don't span R1. It's really easy to span R1. You just have to have some non-zero number in either of the slots. Looks like a smiley face, doesn't it? But we don't. And that's the only way the columns are not going to span. Okay, and so it's this lack of onto-ness that's really deficient. Okay, and that seems to be this case where the level set at that point where you lack that onto-ness, we're having a problem with that. Okay, so for the big to small case, it looks like onto-ness, which we usually get from a wider than it is tall matrix, is what's lacking, and that seems maybe to be what's wrong and why we're creating a non-smooth point there. Okay. Let me do one more example in this part of the video, and then I'll just switch to another video so they're not too long. Example 3, this is going to be another small to big example. Here we're going to go from R2 to R3, and we're going to take f of s and t, and you might wonder why this cone has been sitting there on the left of the screen for a while. Here's where we're going to use it. That's going to be s cos t, s sin t, s. And here s can be negative. This might look like, hey, that looks like polar coordinates. I bet s is not going to be 0. I actually do want s to be positive and negative. Okay, and this creates the double cone that you see over here on the left. Here's the s and t land with its regular rectangular grid, and then here's the image of this parameterized surface in R3. It's a double cone. It's just where x squared plus y squared, oh, that's s squared times the quantity cos squared plus sine squared. Oh, hey, that's s squared, and that's c squared. So it's just our standard double cone. Okay, so clearly the origin is singular here. The cone point here where the two halves of the cone meet, that's very, very singular. Anywhere else but there, if you look at the microscope, it's just a nice, gently curving surface, and the more you put the microscope on, the smaller a little parallelogram you take, the more it looks like just like a single flat plane. Okay, but not at the origin. That's never going to happen. No matter how you magnify the origin, it's going to look exactly the same. It's going to have that conical singularity. Okay, so let's look at the matrix of derivatives. Here we have 3 outputs, 2 inputs. It's going to be 3 rows, 2 columns. And the derivatives, let's see, s cosine t with respect to s is cosine t, and then minus s sine t. And then the second one, we're going to take the derivative with respect to s, that's sine t, and then s cosine t, and then 1, 0. Okay, so let's see, how do we get the origin? It's just put in s equals 0, and t equals anything, actually. That's a weird, that's one of the many weird things about the origin here. Okay, f prime, oops. So f prime at 0, comma, whatever for t is going to be, okay, cosine t, sine t, 1, those don't get affected. But the column of the matrix of derivatives, remember what the second column of the matrix derivatives here, these are the d by dt's. Those are the things that, if I vary the t variable, that's the one that goes around. It's cosine t, sine t. That's the stuff that goes around the circles. It says, what's going to happen when I go around the circle? Well, at the origin, if I try to go around, there's nothing to go around, so I don't move. And that's exactly saying that the velocity vector, the t velocity vector, what our book Stewart often calls, let's see, r sub t vector, that's this guy, it's 0. It doesn't move. And so there's something bad about that. Now, for once, this isn't the 0 matrix. Instead of the first 2 examples where you might have thought, oh, if I get the 0 matrix, that's pretty darn special. It's not the 0 matrix, and it's not any particular matrix necessarily, but it's losing one of the columns. Okay. Now let's think about small to big. Here's a matrix for whatever value of t you put in here. It's a matrix, and that represents a linear transformation, from R2 to R3, there's no way that's going to be onto once again. So onto, who cares? That's irrelevant because it could never be onto. But 1 to 1, yeah, this could have been 1 to 1, and most of the time you're going to get two linearly independent vectors here. In fact, those linearly independent vectors are exactly the velocity curves. They're exactly the tangent curves to the tangent vectors, sorry, to these grid curves. If I vary the s, it goes out from the cone point. If I vary t, it goes around the circles. And so I get this typical picture of two curves crossing, not necessarily perpendicular like they are here, but at least transversely to each other, crossing and not tangent and not neither of them 0. Here, that degenerates to not having those two nice directions. So linearly independent columns, okay? So no for the singular point. For this matrix, we don't get linearly independent columns. We don't get a nice one-to-one matrix, whereas that's something we were getting at most points. Okay. So again, for small to big, it's looking like the lack of one-to-oneness, or equivalently, lack of linearly independent columns, is the crucial feature. We're going to do 2 more examples and try to get this all into a general theory in the next video.